So now we have 2 raised to k r factorial designs. What is R? R is actually for replications. So now if you do each experiment many times, the numbers will be different. So how do you take care of that, and what does it tell? So we will worry about all of the same thing that we did before with replications, computation of effects, variation, tests, and so on and so forth. So the model changes slightly. We have a new term in the model, and that is the E. With 2 raised to k design without any replication, you had 2 raised to k numbers or measurements and 2 raised to k unknowns are the effects. Right? So the number of unknowns was exactly equal to the number of effects, and therefore there was no error. It was a linear equation, you solve it perfectly. And every number will come out exactly as you measured. The prediction will come out exactly as you measured. Right? There was no error. So E term was not there. But now, I'm coming to that. Now, because you measured it many times, and each time the number is different, basically there is something that you are not controlling. There is some noise. And therefore, so now you could have 2 raised to k r experiments. R could be, let's say, 2. You repeat every experiment 2 times, or each experiment 3 times. R could be 2 or 3. Now with that many observations, you have only still 2 raised to k effects. So you have some errors that have some degrees of freedom. In the previous example, in the previous case, the errors had 0 degrees of freedom. Basically, there were no errors. Now you have some errors, and so now we'll worry about that model. Now this is actually, as written, is only 2 raised to 2r experiment. 2 raised to 2r will be 2 factors, but k factors is straightforward. Yeah. All right. So now let us see. It's very straightforward, and we will actually move fast forward in these 1 or 2 chapters because things are very straightforward. So you measured y, it came out 3 times. All you do is get the mean of that measurement, do the table as before, sum it up, get the factors. You get the effects. Okay? And the main thing is that your estimated response would be, basically y hat would be this value plus E would assume 0. So this would be your y hat. Your error will be equal to the difference between y measured minus y hat. And obviously your goal of the model is to have 0 mean error and minimum mean squared error. So the mean error is 0, and this sum of the squares would be minimum when you do exactly what we showed you in the previous slide. When you do this thing in the previous slide, that will give you the minimum squared errors. And so the errors can be calculated for each of the observations by calculating y hat and then subtracting from the observations. So in this case, if there were 3 values measured, the mean was 15, so that is what you are going to predict. Your model will predict y hat 15, and so the error would be 0 in this case, 3 in this case, and minus 3 here. Similarly here the error is minus 3, 0, and 3 because you are subtracting from y measured to y hat. So these are your errors, and as you can see, the errors add up to 0. Actually each row adds up to 0. Right? So they add up to 0, so that is the case, and this is the minimum error you will get. By any other model you will get more errors. For any, let me correct, it's not for any other model. With any other values of the parameters, using the same model. See, if you change the model, the whole thing will change. So let me just say this. If you assume a linear model like this, then the values of q's that will minimize the sum of squared error is that. Okay? If you change the model to something different, which we will see in a minute too, different kind of models. But if you keep this kind of model, then your best bet is to use these values of Q's that we calculated, and this is the minimum squared errors you will get. Now, so we have these errors and we have sum of squared errors. Now we can divide into 5 parts. SST, the total sum of squares, is equal to SSA, SSB, SSC plus SSE. Okay? So you can calculate this way, and then basically these terms, and then you can see what contributes how much. All right, then we can do the percentage variation. Now so let's see, SSY is 27,000, SS0, basically it was y bar squared kind of thing, is 20,000. So the total variation is the difference of these two. SST is SSY minus SS0, which is 7,000. So the total variation in Y is 7,032. Now that can be divided into 5 pieces, or 4 pieces actually. SSA gives you 2 raised to 2 R QA squared. Remember, there is an R term here. So 5,547. SSB gives you 1,083. SSAB gives you 300. And if you add them up, they will add up to 7,000. And with errors, along with the errors. Errors are the remaining of that. So that is, errors is 102. So if you add up these 4 numbers, you will get 7,000. So you can put percentages on them. And you can say that the A explains 78.88%, B explains 15.4%, AB explains 4.27%, the errors explain 1.45%. So the good news is that the errors are very little. What it means is that the factors that you didn't control had very little effect. So that's good. At least you controlled everything. And the second thing it says is that you really want to worry about A more than anything else, because it is 80%, almost 78.88%. Alright, if you have time, then go for B. And then if you have time, then go for interaction AB. Alright. So one thing new with the R replications is that we can calculate the effect of things that we didn't control. Alright. Now, but there are a few more things we can do. First thing is, we can do confidence intervals. But before I do confidence intervals, we need to calculate the degrees of freedom. And I think the best place to calculate the degrees of freedom is right here, maybe. This one, how many degrees of freedom are here? Maybe here. Let's look at here. You see, we are calculating yi minus y hat. For each row, yi minus y hat, if I gave you 2 of them, then you can figure out the third one. Right, because this y hat is calculated from these 3 numbers and not from any of these numbers. So this 15 was calculated from these 3, so if I give you 2 of them and this number, then you know the third one, right? So there are only 2 degrees of freedom. So the errors here have 2 degrees of freedom too. If I gave you any 2, then you can get the third one. So the total degrees of freedom the errors have is 8. 8 degrees of freedom. So, yeah. 2, 2, 2, 2, 2. 4 times 2. Actually, that gives you the formula. 2 raised to 2 times r minus 1 is the degrees of freedom. 2 raised to 2 times r minus 1. This is the number of rows that we had, and r minus 1 is the degrees of freedom for each row. So if you have that, then you can calculate the standard deviation of errors. Standard deviation of errors is simply the sum of errors squared divided by 1 upon the degrees of freedom. And this is also called MSE, mean squared error. So the variance can be calculated by this formula, or mean squared error can be calculated by this formula. Once you have that, you can calculate the confidence intervals of the effects. Okay, we are assuming here that the errors are normally distributed and with zero mean and this standard deviation, and therefore basically you can calculate the effects. So the effects standard deviation is SE upon square root of 2 raised to 2R, which is actually basically 12 in the previous example. 2 raised to 2 is 4 times 3. 3 is the replication, square root of 12. So each of these effects have same standard deviation, and therefore confidence interval is simply the mean minus plus t value times the standard deviation. If the confidence interval does not include a 0, then it is significant. Okay, not important, significant. And we will see this kind of stuff in the example in a minute. So for the memory cache study, SE would come out 102, which was the sum of squared errors, divided by 2 raised to 2 times R minus 1. R is 3, so that is 8. 8 degree, actually 8 was also degree of freedom. So that is MSE is 12.75. Square root of that is 3.57, which is the standard deviation of errors. For the effects, it is further divided by square root of 12, so we get 1.03. For 90% confidence interval with 8 degrees of freedom. For 90% confidence interval, we read t value at 9.5 and 8 degrees of freedom, which is 1.86. And the confidence intervals come out like this. None of them are 0. So all of them are significant. This will be in the Excel worksheet, so you really don't have to worry about it. I just put the value R here and you get it. And this is not a calculation. The calculation is simply calculating SSE. That you just have to decide how you do SSE. Degree of freedom is 2 raised to 2 R minus 1 times R minus 1.
Yeah, but you also counted them from the table.
Yeah, so exactly the same thing. It will come out the same.
I know, but why did you do the table?
Oh, I just wanted to explain to you.
I see.
The table explains. This one doesn't explain. This is just a formula here, right? So why did I put R 2 raised to 2 R minus 1 here is because there are 2 raised to 2 rows. Each row adds up to 0, and therefore it has R minus 1 degrees of freedom. Let me just say it again. Each row has 2 degrees of freedom. So I said 4 times 2 is 8. So you don't have to calculate it from the table. You have to understand from the table that how 8 number came about. So the key thing is that all of these parameters are significant, and a statistician will tell you that you shouldn't ignore any of these. They're all significant. All right, but let's become an engineer. And as an engineer, we would say, what percentage does it really explain? All right, so QA square and QB square and QC square, I don't have the numbers here, but I can tell you that this is like 20 and this is like 10. QA is 4 times more variation explaining than in B, right? And then B is explaining about 9 times more than the interaction. So, the A is really the most important parameter. And depending upon QAB, I don't know what percentage it is, but this could be unimportant. It's very small percentage, right? Even though it is significant, statistically significant, but if I had a choice, I would spend time there. If I have more time, I will spend time here. If I have more time, I will spend time there. What you're saying is that you did not do either enough replications or something, so you cannot be very confident. So you're making a statement like this: oh, this factor A has 80% of the variation, but I don't know about that 80% because it is not significant. Right? So that means you really didn't do enough replications and things like that. So you will find that out. Then only your confidence will be so wide that it will include a 0 for a large value like 80%. Right? So that can happen, but I mean that's rare. Generally the most important parameter will generally be significant, because for that to include a 0 means everything else will include a 0. Okay. You see, all of them have the same breadth. 39 to 42, 19 to 23, they have the same breadth. Right? So if this includes a 0, then And if this is so wide and it is big, then all of them will be 0. And then you will say, well, there is something I have missed here, which is that you have lots of errors. You have lots of errors.
So you basically just didn't do experiment.
Yeah, actually, I think what most likely will happen in that kind of experiment, that the errors will explain 80% of the variation, and your model explains 20% variation. And out of that 20%, maybe 15% goes to A, 5% goes to B, so there is small percentage. Errors would be the most percentage. Okay, Q0 is not explaining anything. By the way, Q0 is the mean. Yes, if you want to call that explaining, Q0 is the mean. And so if you didn't want to use any of this model, and you just wanted to use, like we talked about in regression, what is B0? B0 was the mean. If you didn't want to use any factors, then you can simply take the mean of all 12 observations and say, well, here is my model and here is my prediction. Just the mean. Everything is noise. So Q0 is actually simply the mean. So that is like, if you had 0 factors, so that is a Q0. Okay. All right. Now the interesting thing is you can do confidence intervals. See, the one part is that everything that is you are doing in the measurement is random. So we talked about mean is random. Then we talked about the parameters are random. Now you could have some functions of parameters. And oftentimes people want to do some contrast. What is a contrast? Contrast is defined as some linear combination so that the coefficients add up to 0. And you will see in a minute. But before I go to the contrast, if you take any q values, don't have to be all of them, some q values, and you multiply them with some factor h, and you add them up such that the h adds up to 0. First of all, h adds up to 0, then this thing is called a contrast. So variance of the contrast can be used by this formula, and you can use the same t interval as before. Alright, so let me give you an example of a contrast. So let's say you want to measure the QA plus QB minus 2QAB. Why? I don't know, but for some reason. And we'll see some valid one. This one is actually totally just an example here. So the coefficients are 1, 1 and minus 2, they add up to 0. So this is a contrast. So the mean of this contrast, U, is QA plus QB minus 2 times the mean of QAB. And that will come out to 21 because you know QA, you know QB, and you know QAB. Variance will be used by that formula that we just had a minute ago, which was SE square times sum of HI squares. Sum of HI squares. SE square times sum of HI square divided by 2 raised to 2R. So in this case, SE square times sum of HI square, 1 square plus 1 square plus 4 square, plus 2 square is 6. So that is the 6. Is this number 6 comes from 1 square plus 1 square plus 2 square. So you put HI squares here, sum of HI squares, and then divide by the total observations, 2 raised to 2 times R, 12. This is the variance. Standard deviation is just the square root of that. And then you take the t value as before and get the confidence interval, so it's still significant. Yeah, this is just an example. Actually, a more common thing would be simply QA minus QB. QA minus QB is a contrast. It starts up to 0. Right? And why would you be interested in QA minus QB? Because you want to see the difference between the effects of A and B. So QA minus QB would be more representative example of what you would use. But here I just added up QAB just to show you an example. You can apply here too. Alright, now you could do the same thing for predictions. When you predict, you will be predicting the mean. Y hat is actually exactly this because error is 0. But this y hat is a random number. Its standard deviation depends upon how many observations will you take. So mean of m responses will have this formula. where the n effective is the effective degrees of freedom, which is the total number of runs divided by 1 plus sum of degrees of freedom used in y hat. In y hat, this one had 1 degree of, so basically 1 plus sum of degrees of freedom used in y hat, n effective. Okay, total number of runs is 2 raised to 2 times r, and the number of degrees of freedom in the parameters. So we used 1, 2, 3, 4 parameters. Each of them have 1 degree freedom, and therefore you have 5 here. Confidence interval same way, just with t values, and the m is the number of observations that you will take in the future. If you just take one observation, you put m equal to 1. If you take infinite observations, you put m equal to infinity, and that term will go away. So the example is memory cache study, and you want to predict what will happen with xa minus 1. You have already measured. This is here the thing, and this is more of an example here because you have already measured 3 times the value. Now you are going to predict. Your prediction is going to be exactly the same mean. The main thing is that if you want to be sure that in the future that mean shows up, then you have to say how many observations you will take. If in the future you are just going to take 1 observation, then your standard, your variation will be large, and that would be 4.25. Your confidence interval would be this. Alright, you have already measured 15 out of 3, but basically now your confidence interval says that the next measurement that you take, the 4th one, could be anywhere from 7 to 22. On the other hand, well, if you are going to take 5 experiments, just for the sake of it, 5 more, so you have already have 3, and based upon that you are predicting 15. Well, that would be, if you are going to take 5 more, then your confidence interval would be this, 9 to 20. So the mean of 5 will lie in that interval, 90% time. If you are just going to take large number of observations, not 5 more, then your confidence will be this much, and so on and so forth. You can keep going. Okay, so basically 3 observations is a small number. Now large number means, suppose, whatever number. I mean, basically theoretically it is infinity, but somewhere close to infinity. If you take, now here I think, having said that, you really don't need infinity because 1 upon m has little effect, not too much. So here I think, let me just say this. If you put m equal to 100, alright, 5 by 12 is like half, and 1 upon 100 is 0.01. It will be close to infinity. Okay? So basically what I am doing here is going over everything that we did in regression, redoing here with 2 raised to 2 experiments, and now with 2 raised to k experiments in a minute. Alright, so let's see, where are we? So we did the confidence interval. There is one more thing here which I want to bring out here is, suppose you don't want to do the future measurements, you just want to say that the mean is 15. Then this formula will become basically, this is the confidence, this is your standard deviation, and this is your confidence interval. And the formula can also be thought of as a contrast formula where you use this model, the model which is the original model like this. This is a contrast because they add up to 0. If you add up 1 plus xa plus xb plus xab, they add up to 0 for all values. You see here in this row, every row adds up to 0. 1 minus 1 minus 1 to 1, 0. Current mean response for each row is going to basically have this formula which is going to add up to xa plus xb plus xab. The QAs will add up to 0, not the XAs. QAs will add up to 0. So basically this is, so for that the HIs will become equal to 4. Some of these HIs will become add up to 4. HI squares, 1 square plus 1 square plus 1 square plus 1 square 4 times. And then you get this standard deviation using the contrast formula and you get the confidence interval for the current mean for that row. All right, so now we have a homework. Let's see. This is just a repeat of 2 raised to 3 design, 2 raised to 2 times 3 design. So we have 3 values of A, 3 values of basically 2 factors, A and B. And you have to prepare the table and do the effect. Now let's see, it says determine the effect. So this is kind of simple. We should have more than this. So this one is simply saying that you determine the effect. So all you have to do is find out Q naught through QAB.